Okay, so let's look at problem 8. So define the geometric sequence recursively and by a formula. This is in the book, so you just need to try to find it. Part B, factorial, same, it's in the book. Part C, it's in the book, so it'll take some time, but you'll have to find it. And you're going to just have to know these. Just commit them. Essentially, they're examples that are so important because they're just going to come up again and again and again. Make them your friends. Okay, and then they will help you in the future. Part D. So first it just gives an amazing formula, and then it says, please prove that this formula satisfies the recurrence equations. So the hard part of this problem is, what does that mean? What do I have to prove? Well, to satisfy the recurrence equations of the Fibonacci sequence means that, let's call this number z sub n. The recurrence equation for the Fibonacci sequence is this equation. Every number is the sum of the previous two. Okay? And so what I suggest is look up Vihart's video on plants and Fibonacci and on YouTube, and you will see that it's, well, if you watch an hour of amazing stuff, or just watch the first 5 minutes, this number, these numbers come up, and they explain why this sequence occurs in pineapples, and why it occurs in pine cones and in flower petals. Anyway, we need to prove this. So first, what I'm just going to do is say, well, if we can show that zn minus 1 plus zn minus 2 minus zn, if we can show that that is equal to 0, maybe it's easier to see over here. Show this, then we're done. Okay? Because if this equals 0, then this equation is satisfied. And we need to show that for any n. So n is just going to stick around as a variable. Okay, so I have no idea how we're going to do that, so let's just plug in. So z to the n sub n minus 1 is this formula up here. First of all, let's notice that we can just factor out a 1 over square root of 5. And I'm going to get tired of writing it, so I'm just going to say 1 over of square root. And secretly, there's a 5 there. So I'm going to factor it out, and then z to the z sub n minus 1 is 1 plus squiggle over 2 to the n minus 1 minus 1 minus squiggle over 2 to the n minus 1. Pause to make sure you see where I got that. Now I have the z sub n minus 2, so that one is just raised to the n minus 2. Okay, and one last thing, I have to subtract zn. So I'm going to subtract pause the video and just see that what I did here was no thinking. I'm just plugging in, and I'm just going to see what happens when I replace these with this explicit formula. Staring at this for a while, you'll realize that there's a power of n minus 2, and in particular, there are things that are either blue or, let's make them green. The ones with the minus signs, let's make those green, so that you can see what's going to happen here. So the blue ones, I can factor out a 1 plus over 2 to the n minus 2 from each of them, because that's the lowest power of that thing that occurs. And what I'll have left over is 3 terms. What are those 3 terms? Well, they are, if I pull out n minus 2, I have 1 power of that left over. If If I pull out an n minus 2, I have a plus 1 left over. If I pull out an n minus 2, I have 2 of those left over. Okay, and then I'm not done. I still have the green. And what I'm going to do is, I don't know, I guess I'll say plus 1 minus root 5 over 2 to the n minus 2. I'm going to pull that out of this one, and I get a minus I pull that out of this one. Notice this has a minus sign, and I'm going to get a minus 1. And I pull it out of this one. I have two factors left over with a plus sign. Okay, and that all I've done is I've recognized there are common factors. Pause the video until you see what I did. Okay. And now what I'm going to do is just look at this formula. Let's take this formula and just see what it does. Let's focus in on it. I have a 1/2 plus a square root of 5 over 2 plus 1 minus, and now I have to square this thing. Okay, I can square it. 1 plus 2 root 5 plus 5 over 4. Okay, so now I have to simplify. Let's see what I get. Plus root 5, 2, plus 1, minus a fourth, minus root 5 over 2. Oh, wait. Let's do the 1 and the 5 together. That's a 6. So 6/4 is 3/2. I'm going to get minus 3/2. Okay. Now look at this. I have a 1/2, 1, and minus 3/2. That is 0. And then I have a plus root 5 over 2, minus root 5 over 2, and that is 0. And so this entire thing in the purple is 0. That means that this entire term is 0. Okay? Wow. Let's check what this thing is. So, okay. This part is sort of annoying, but I can do it. Minus a 1/2 plus root 5 over 2. Okay, that's that. Now I have minus 1. And then I have to square this thing. Okay, so I can do that. So plus 1 minus 2 square root of 5 plus 5 over 2 squared is 4. Do you notice how good you have to be good at squaring things? Like, you need to practice. If you have a plus b, then you need to be able to square it, no matter what a is and no matter what b is. And that's no different if there's a 2 down there. You just have to be good at this and practice this. Like, if that was hard, do this a bunch of times. You know, for an hour. Maybe do that for an hour. And maybe raise it to, maybe do a plus b to the 3rd for an hour. Okay. Now, what do I have here? So the 1 plus 5 brings a 6 again, which means I have a 3/2 and a minus root 5 over 2. That's this piece. And now I look and I say, look, I have plus 3/2 minus a 1/2 minus 1. That is 0. And look, I have minus root 5 plus root 5. That is 0, and the whole thing is 0. And so therefore, I am done. Therefore, this formula does satisfy the recurrence equation for all n. You see, it worked for all n. What I was able to do is pull out almost all of the factors, okay? And then what remained was 0. Okay. So that proved that this is an explicit formula for the Fibonacci sequence, which before we could only define recursively, which meant as a sequence that satisfies infinitely many equations, and we happen to know the first few values of that sequence. Okay. This is sort of like if you had the equation of a curve, and you knew that all the points on the curve satisfy that equation, but you wanted to say, well, I want to generate points. I want an explicit formula for points on that curve. What is that explicit formula? Well, you can discover it like this one works. Okay, but in general, it's very hard to produce this explicit formula given equations. Here we had given equations for Fibonacci sequence, and we had produced an explicit formula. Well, actually, we didn't produce this formula. I just gave it to you, and you verified that it was correct. Okay, so that's sort of like taking this cos and sine and plugging in to the equation, and just verifying that, oh yeah, that is true. Yeah. So and then you verified that this is a corrective formula, generating points on this equation. All right, that's problem 8.